Assalamu alaikum everyone, this is Tofail Kareem. Welcome to the first lecture, The Basics of Antenna Technology. In this first video, we will discuss what an antenna is, antenna types, antenna's radiation and working principles, crucial parameters and applications. So let's dive deep into the topic. So what is an antenna? The first question that rises in our mind when we talk about antenna technology. Well, an antenna is a device used to transmit and receive electromagnetic waves. It is analogous to a transducer, as transducers convert one form of energy to another. An antenna converts electrical energy into electromagnetic waves and vice versa. According to radiation pattern, there are primarily two types of antenna available: isotropic or omnidirectional and directional antenna. An omnidirectional antenna is such an antenna that radiates equally in all directions. To be more precise, the radiation intensity of an omnidirectional antenna is constant in all directions. In contrast, a directional antenna can radiate or receives power only from a particular direction. There are many types of antennas available nowadays. Here we see some basic types of antennas, including the dipole antenna, helical antenna, and Yagi-Uda antenna, which is known as TV antenna to most of us, the microstrip patch antenna, the waveguide antenna, and the reflector antenna, which we know by the name of the dish antenna. Now the question is how an antenna radiates. To create radiation, there must be a time-varying current or an acceleration of charge, so we need a source that will force the charge into motion. Now, as we have learned how radiation occurs, still we need to know how the guided waves or EM waves are detached from the antenna. Before we attempt to explain that, let us draw a parallel between the guided and free space waves and water waves created by the dropping of a pebble in a calm body of water or initiated in some other manner. Once the disturbance in the water has been initiated, water waves are created which begin to travel outwardly. If the disturbance has been removed, the waves do not stop or extinguish themselves but continue their course of travel. If the disturbance persists, new waves are continuously created which lag in their travel behind the others. The same is true with the electromagnetic waves created by an electric disturbance. If the initial electric disturbance by the source is of short duration, the created electromagnetic waves travel inside the transmission line, then into the antenna, and finally are radiated as free space waves, even if the electric source has ceased to exist. When the electromagnetic waves are within the transmission line and antenna, their existence is associated with the presence of the charges inside the conductors. However, when the waves are radiated, they form closed loops and there are no charges to sustain their existence. This leads us to conclude that electric charges are required to excite the fields but are not needed to sustain them and may exist in their absence. This is in direct analogy with water waves. Now we will talk about the working principle of an antenna. The fundamental concepts from previous slides give a clear realization of antenna working principle. Let's recall the process. When an alternating current is applied to the antenna, it causes the electrons in the antenna's conductive elements to move back and forth. The movement of electrons creates an oscillating electric field around the antenna. This electric field extends outwards from the antenna and fluctuates with the frequency of the AC current. As per Maxwell's equation, a changing electric field induces a changing magnetic field. In the case of an antenna, the oscillating electric field causes an oscillating magnetic field to form around it. The magnetic field is perpendicular to the electric field and also oscillates at the same frequency. The combination of the oscillating electric and magnetic fields results in the creation of an electromagnetic wave. These waves are composed of perpendicular electric and magnetic fields that propagate away from the antenna at the speed of light in free space. Now let's move on to some crucial antenna parameters. The parameter that we'll look at first is the return loss, or S11, which is a critical parameter used to characterize the performance of an antenna or any other two-port network. It quantifies the amount of power that is reflected back to the source when an electromagnetic wave is incident on the antenna. It also indicates the bandwidth of the antenna. The range of frequencies for which return loss is less than -10 dB determines the bandwidth of the antenna. Another important parameter is voltage standing wave ratio, or VSWR. VSWR indicates the impedance matching of the antenna and the system. From the maximum power transfer theorem, we come to know that when two systems have identical impedance, the maximum amount of power transfers from one system to another. VSWR should be 1, but in the real world, any value up to 2 is acceptable. Gain is also a crucial parameter in terms of antenna. Antenna gain refers to the amount of power that is transmitted toward the peak radiation direction compared to that of an isotropic source. The bandwidth of an antenna refers to the range of frequencies over which the antenna can efficiently transmit or receive electromagnetic waves. It is a critical parameter that characterizes the ability of an antenna to work effectively across a specific frequency range. Polarization is another important parameter for an antenna. The polarization of an antenna refers to the orientation of the electric field vector of the electromagnetic waves it radiates or receives. It is a crucial parameter that determines how the antenna interacts with other antennas or electromagnetic fields in its vicinity. Now, the last important parameter of an antenna is the radiation pattern. A radiation pattern is a graphical representation that describes how an antenna radiates or receives electromagnetic waves in three-dimensional space. It shows the relative strength and direction of the radiated or received electromagnetic field from the antenna. Radiation patterns are crucial in understanding the antenna's directional characteristics, coverage area, and overall performance. Now let's move on to the applications of antenna technology. Antenna technology plays a crucial role in various applications across different industries. Its ability to transmit and receive electromagnetic waves efficiently enables a wide range of wireless communication, sensing, and tracking systems. Some of the key applications of antenna technology include wireless communication, broadcasting, radar systems, satellite communication, wireless sensor networks, mobile devices, RFID, aerospace and aviation, medical devices, and military and defense. Thank you for being with us, and stay tuned to have more updates on this tutorial series.